Okay, so our constraint algebra, and when we get quantized, so this is not exactly the same kind of constraint algebra as the classical level, but you have to include firstly the discretization corrections and quantum corrections. So these come from this, of course, the discretization corrections coming from the fact that we actually we are not really quantizing the quantity. We are not really quantizing the quantity on the continuum. We are actually firstly put those constraints on the lattice. We write the discretized formula for those constraints, for these constraints, and then quantizing those lattice formulation, quantizing the lattice formulation. Yeah, that's why we get some discretization corrections of order mu. And secondly, and because of the quantization, classically something becomes commutative. Two functions are commutative, but at the quantum level, it's become non-commutative. That's why you get another correction, which is a quantum correction of order h bar. So here it is this our actual situation. So now, so these two terms are usually called anomaly. Yeah, so this term, more precisely, this term proportional to h bar is called quantum anomaly, and the term proportional to mu is called discretization anomaly. All right, so now suppose our constraint algebra, quantum constraint algebra is of this type. What will happen? Okay, so now let's repeat our procedure. So suppose we find the solution of constraint equation given our procedure that Ci half operator psi equals to 0. Yeah. Suppose we can, I mean, although we have a problem 1, solving those constraints are hard, but suppose we are able to solve these quantum constraints. And what will happen? So left-hand side, again, given the solution, we let the left-hand side of this constraint algebra and right-hand side of this constraint algebra operating on the state. So firstly, the left-hand side, Ci Cj operating on psi is still equals to 0. Yeah, because it's still because it is a solution of constraint. It's still equals to 0. But right-hand side, okay, hat ijk ck plus mu 1 hat plus O2 hat. So these act on psi. Okay, so clearly it is not 0, right? And the first term will give you 0 equals to mu O1 hat plus h bar O2 hat psi. It is not equals to 0. Okay, apparently it is not consistent. Yeah. So it means that our procedure fails. Let's look at our earlier naive proposal. Is that the proposal is that we are going to look at solutions of the constraints, and those constraints will span the Hilbert space. Yeah, and the Hilbert space will be our goal. But now we find well, when we look at constraint algebra, we find inconsistent results. Right. So when we compute the commutator of constraint, it equals to 0, but the right hand side it is not equals to 0. Okay. Well, however, we can remove this inconsistency by adding some more constraints. Yeah. By requiring the this term. This quantity, this operator O1 and O2 individually act on psi equals to 0. Okay, so then it will become consistent. So this inconsistency inconsistency. So we got inconsistency unless we impose in addition that O1 hat eigenpsi equals to O2 hat equals to 0. So which means we get two additional, well, so actually this is not only two equations, but 2 times infinity equation, because here it has index ij. So in principle here you have index ij. Index ij. So I just skipped this index ij. Okay. So therefore this O1 and O2, they are 2 times infinity operators. Yeah. So you got 2 times infinity. Well, you got infinite, another set of infinite constraints. So firstly, but then it caused even more problems because these two constraint equations are again hard to solve. It's probably even harder than the earlier diffeomorphism constraint equation and Hamiltonian constraint equation, because this O1 and O2 they are usually highly complicated operators. So firstly, hard to solve. So yeah, hard to solve. And this equation, those equation has no classical analog. So because O1 and O2 classically they are not zero on the phase space, but yeah, suddenly at the quantum level you require them to be zero. Has no classical analog. Okay, so then it seems that we are actually imposing too many constraints, yeah, because you classically you only have C and Cj equals to 0, then quantum mechanically, but quantum mechanically you not only impose C and Cj equals to 0, but also you impose those O1 and O2 equals to 0. So you get too many constraints. Many constraints. Many quantum constraints. Yeah, and then it leads to that the solution space is too small. So, which is our physical Hilbert space. Okay. Okay, so this is really a problem coming from quantum anomaly, come from anomaly at the quantum level. Okay, so so whenever we find that the constraint algebra at the quantum level, which is different from the classical constraint algebra, and you get additional terms, and it means that you have constraint anomaly. And then whenever you have constraint anomaly, well, the equation become, this constraint algebra become inconsistent at quantum level unless you impose some additional constraint. But when you impose additional constraints, you get much less solutions. Your solution space may be too small, and so the entire procedure become problematic. Okay, so well, the conclusion is that constraint anomaly is problematic. Okay, all right. So how to understand those constraint anomaly, and how to get rid of them. So let's talk about those constraint anomaly in general. So maybe for most of you, I guess you don't really familiar with what is called anomaly. Yeah. So let me first talk about what are quantum anomaly in general, and in quantum, especially in quantum field theory, and also for general quantum system. Okay, so in one sentence, so-called anomaly is that you have some symmetry which is classical, which is preserved classically, but get broken quantum mechanically. Yeah. So whenever you break your symmetry by quantum effect, and this is called anomaly. Okay. So let's look at some general perspective of anomaly in quantum field theory. So in general, let's talk about quantum field theory. Well, in quantum field theory, as we know that you have usually global, sometimes you have global symmetry and sometimes you have local symmetry. So let's firstly talk about global symmetry. Global symmetry. Well, global symmetry is that classically you have some symmetry charges, and those symmetry charges satisfy some Poisson bracket. So let's call those symmetry charges Q, and you have Poisson brackets between those symmetry charges QK. Okay, and so let's assume that the classical symmetry algebra is just a Lie algebra. Okay, so this F is just a constant. Constant. So it means that Lie algebra. Okay, and for example, this Q can be well, so this is the symmetry charge. For example, things like, for example, your Hamiltonian, yeah, and or your momentum, right, and or angular momentum, J. Okay, so it can be in your quantum field theory, your total Hamiltonian or total momentum or total angular momentum, which is some symmetry charge of your field. Then yeah, it satisfies some commutation relation. And in case, for example, the commutation, the Poisson bracket between Hamiltonian and momentum is 0 in case your momentum is conserved. Yeah, your momentum is conserved. Well, Hamiltonian commutation relation with J with angular momentum is 0 in case your angular momentum is conserved, right? So classically, you get a lot of these kind of symmetry charges. Whenever you have a symmetry, you have a conserved quantity, right? And you get a lot of these kind of symmetry charges like Hamiltonian, momentum, angular momentum. And also, sometimes you get local symmetries, right? You have symmetries like U1 symmetry of scalar field, complex scalar field, or Maxwell field. You get also some U1 symmetry. Okay. All right. So now when we classically, these are classical symmetry algebra, so which is perfectly like the Lie algebra. So in that case, and now when we quantize at the quantum theory, and those commutation Poisson bracket of symmetry charges become commutators. Ui, J, and those symmetry charges are operators, like your Hamiltonian become Hamiltonian operator, momentum become momentum operator, right? But in general, when you do the quantization, in some ideal case, again, the optimistic case or ideal case, you get still this kind of symmetry algebra at the quantum level. But in general, it's not always true. Although in things like free field theory, if you talk about Hamiltonian operator, momentum operator, angular momentum operator, they will, the quantum algebra preserves the, still very similar to the classical Poisson algebra, but it is not in general, especially when you consider some complicated interacting quantum field theory. So in general, you may have some quantum corrections. And these quantum corrections is usually called quantum anomaly, quantum symmetry anomaly. Correction here is called quantum anomaly. Quantum anomaly. So it means that classically you have a symmetry. Well, then quantum mechanically, this symmetry algebra is not true anymore. And why it happens that you always have a well, you can have a quantum correction. The reason is very easy. It is because so the origin of the anomaly is just because in quantum mechanics, state psi is the same, or is equivalent to psi up to a phase. So I mean, quantum mechanics and the probability interpretation of your states is determined up to a phase. Okay? So therefore, physically, psi is equivalent to e to the I theta multiplied psi. Therefore, suppose you let your operator commutation relation of your symmetry charges put it on the exponential. You consider some translation or some symmetry, finite symmetry transformation generated by the left-hand side of this equation, operating on certain state psi. Okay, and it can happen that it equals to the right-hand side e qk epsilon psi. So I mean, in most of the cases, well, in some good cases, simple cases, this will be the result. And if you have commutator exponential epsilon psi, it's a finite symmetry transformation. Yeah, it equals to some structure constant up down qk epsilon psi. Yeah, so in many cases it is true, but in some complicated cases it is not true, but up to a phase. But physically it's still true, right? It's still, I mean, it's still like a symmetry, but it's just because quantum mechanically everything can be different up to a phase. Okay, and because of this phase, you get this quantum correction. Yeah, this phase is usually of order h bar, and you can see that, and when you act on state, generically the commutator does not equals to fijk times qk, but yeah, you get some other contribution coming from space. So this is quantum mechanical origin of symmetry anomaly. Okay, and this is in many quantum field theories, and the people has discovered this kind of quantum anomaly. People have even in experiments and phenomenology, people understand this kind of symmetry anomaly already. So this is just a symmetry broken by quantum effect, right? So I mean, of course, you can imagine that classically have some properties, but some property is not going to preserve at the quantum level because it will be broken by quantum effect. Symmetry broken by quantum effect. Quantum effect is called a quantum anomaly. Well, another easy example, one example. Well, one standard example is called a axial anomaly in quantum field theory, or triangle anomaly. When you talk about gauge theory coupled to fermion, so this is one standard anomaly. Well, and this by quantum effect is called quantum anomaly, and this case a symmetry anomaly is usually phi. Is phi. So it is not really a big problem in case it is a symmetry anomaly. In case it is a global symmetry and broken by quantum effect. And it is well studied. And for example, a standard example in quantum field theory context is called axial anomaly. Yeah, or sometimes it's called triangle anomaly. That means the same thing. Okay. Another standard example is that is the scaling broken quantum effect break the scaling invariant, because for example in gauge theory, where gauge theory coupled to matter, coupled to fermion or scalars, and the Lagrangian classically is scaling invariant. Yeah, and up to if you impose different fields some scaling weight, and the classical Lagrangian is scaling invariant. But at the quantum level, it is not. Yeah, and because you get a beta function, the theory is asymptotically free, and at different energy level, at different scale, the theory behaves very different. The QCD at ultraviolet and QCD at infrared is very different. Yeah. So it is again, it's an effect of the quantum. It's a quantum effect which breaking the scaling invariant. Yeah. So quantum axial anomaly or scaling breaking scaling invariant in quantum field theory. Okay, so this is usually what happens in quantum field theory, in quantum field. Okay, and whenever you have a global symmetry at classical level, in many cases it will be broken by the quantum effect. And whenever the symmetry is broken, this is called an anomaly. Okay, but this is for global symmetry. But the global symmetry broken by quantum effect, it is fine. So people get used to that already. But for gauge symmetry, so there are different symmetries, what we call gauge symmetry. It is a different story. Okay, for gauge symmetry, and our previous symmetry charge Qi, now it is actually our constraint, right? The symmetry charge, for global symmetry, what we call Q, and now for gauge symmetry, they are C, they are constrained. But in this case, the anomaly, again, but the same story. Yeah, I mean, classically we have Poisson algebra, we have classical symmetry, but at the quantum level, well, and because of the quantum effect, you get some broken symmetry. Yeah, the symmetry is broken. In many cases, dynamically, it becomes broken. But then the quantum anomaly which breaks the gauge symmetry, it is called a gauge anomaly, or it's called constraint anomaly. Which is just exactly what we discussed earlier. But the gauge anomaly, it is not fine. Gauge anomaly or constraint anomaly. Constraint anomaly. Although it can happen, right? It's exactly the same logic as we discussing this global symmetry, and you have a classical commutation relation, classical Poisson bracket between symmetry charges. You get some Lie algebra, but quantum mechanically, you get quantum corrections in your commutation relation. But therefore, in gauge symmetry, for gauge symmetry, is usually also broken by quantum effect. But in this case, it is not fine. You get a problem. Right? So therefore, in gauge theory, usually you try to avoid the gauge anomaly. In many cases, and for example, in standard model, when you show that standard model is really consistent, you have to show that you have no gauge anomaly. Yeah. The gauge anomaly is actually cancelled by species of quarks. Well, probably in standard model, it's not a chiral theory. but suppose you have a chiral, version of the quantum field theory. Well, anyway, so whenever you you define a quantum field theory, define a gauge theory, you have to make sure that you have no gauge anomaly. Okay, but but in general, well, in many cases, you are not able to show that you have no gauge anomaly at all. Gauge anomaly appears anyway, because well, because the constraints, when you quantize, you get a quantum correction. Well, because when you quantize the constraint, Ci Cj equals to Ijk Ck plus H bar or hat. So for simplicity, we still assume it is constraint. It is classically a Lie algebra. So Fijk is a constant, but anyway, you may get a quantum correction in your constraint algebra. Yeah, and then whenever you find the quantum correction by the previous argument, so it leads to additional constraints. Constraint O hat of psi equals to 0, right? And then it means that your physical Hilbert space is too small. Usually it's too small. Yeah, you don't have the physical Hilbert space is too small. It means that you don't have enough states to study physics. Yeah, especially it may be that you don't have enough semi-classical states. Okay. All right. And moreover, in our case, it is even the situation is even worse because we have not only quantum anomaly but also discretization anomaly. We have both discretization anomaly and quantum anomaly. Okay, so in many cases, yeah, especially when we talk about quantum gravity and related topic, you usually get those anomalies anyway. So there's no, it's very hard to show that you can get rid of those anomalies. In standard quantum field theory, in gauge theory, in many cases you can find some cancellation to get rid of those quantum anomalies. Yeah, and so it means that our quantization procedure gets some problem. Yeah, and it sounds like really frustrating, but and moreover, and there's no better way to quantize. You may wonder, well, maybe there should be some better way to quantize Hamiltonian constraint and diffeomorphism constraint, so that you get rid of those anomalies. But the truth is that in people study this field for 20 years, there's no better proposal to do the quantization. So far, there's no better proposal. To quantize Hamiltonian constraint and diffeomorphism constraint. Okay, so we have to accept those quantization, and we have to accept that they are constraints. They are constraint anomalies, at least at current state. Okay, and all right. So now the question is how to accept this situation and still make progress. How to accept anomaly. But make physical hyperspace not so small. Okay, so now ultimately the problem of constraint anomaly is that physical hyperspace is too small. Okay, but somehow should we look for some better procedure to impose those constraints such that in the end physical hyperspace is not small, although we have anomaly. Yeah. So in case, because now we have anomaly, if we impose constraint naively, we will get physical hyperspace too small, but probably we need to find a better procedure to impose a constraint so that physical hyperspace is not that small. Okay. So the idea is that we have to impose a constraint weakly. Weakly impose a constraint. Weakly impose using quantum constraint. Quantum constraint. Okay. So what we mean by weakly imposed constraint? So firstly, what is a strongly imposed quantum constraint? Our naive procedure is called strongly imposed constraint. Strongly imposing those constraints. It is just looking for solutions of this constraint equation. Yeah. Okay, so firstly, psi belongs to hyperspace, and we impose this constraint strongly to the hyperspace and looking for solutions. Psi span the physical hyperspace. Okay, so this is called strongly impose the constraint. You just you have the constraint operator and you're looking for the solution of this equation. Okay. And looking for solution of this equation, and the solution spans the physical hyperspace. This is called strongly imposing constraint. And now what is weakly imposing constraint? So there are two procedures of weakly imposing constraint. And so firstly, I'm going to talk about a standard way to weakly imposing constraint, and then I will talk about a non-standard way, which is used in Lupin gravity to weakly impose constraint. So firstly, it is a more standard procedure. It is called Gupta-Fowler formalism. Gupta-Fowler formalism. So this formalism is even used. So this is a very standard procedure. It is used in, for example, in quantizing electromagnetism. Yeah. So what is this formalism gives? So we are looking for. So we are not really imposing strongly the constraint on the hyperspace, but looking for some weak solutions. Namely, we're looking for a subspace. Again, I call H physics, but I put a W. That means weak solutions inside the original hyperspace, such that for any psi phi, for any pair psi phi belongs to this subspace. Okay, belongs to the subspace. The matrix element of constraint operator becomes to 0. Okay, vanishes. The matrix element vanishes. Okay, so how you can see this is weak, is weaker than strongly imposing constraint, because this part, it is just a constraint operating on state. But when we're looking for weak solutions, this part is not necessarily 0. Not necessarily 0. Okay, because it can be just orthogonal to the other state. Right, orthogonal to psi. Which physics? Okay. But when you're strongly imposing constraints, and this part has to be 0. So the constraint operating on state has to be exactly 0, have to be strongly 0. But when you impose them weakly, when you impose constraint weakly, this not necessarily 0. The only requirement is that the constraint operating maps the state to the orthogonal complement of the physical Hilbert space, the weak physical Hilbert space. So the constraint operating on state in the solution space is not necessarily 0, but you only need to map it outside the Hilbert space. Okay, so that's why you can see this is really weaker. It is much weaker. You can really get a lot of solutions. Although when you're imposing strongly constraints, you have no solution, but weakly you can indeed get solution. And this procedure, it is used, for example, in string theory. So it is used in for example, so the very first example is the quantization of the electromagnetic field. It is also used in so-called covariant quantization of string. Covariant quantization of string. Okay. All right. But still, this is not exactly what we do in loop quantum gravity. So in loop quantum gravity, we work on we use the second procedure of weakly imposing the constraint. This is called master constraint formalism. Master constraint formalism. Master constraint formalism, and this is invented by Thomas Tiemann in 2003. Okay. The idea is that classically we're looking for some classical equivalent constraint which somehow better than by the earlier constraints. So firstly, we define a classical master constraint. Classical master constraint. Master constraint, and the master constraint is only a single constraint. It's not a infinite number of constraints. But okay, so let me first write down the master constraint. Q and C square